In this video, we will look at other methods to compute the Thevenin or Norton resistance. The three circuits shown on the top are equivalent to each other at the terminals A and B. The first circuit is any arbitrary circuit made up of resistors, independent and dependent sources. The second circuit is the Thevenin equivalent of that circuit, and the last circuit is the Norton equivalent, which is equivalent to the other two circuits. In a previous video, we gave methods to compute the Thevenin voltage Vt and the Thevenin resistance Rt, or the Norton current Jn and the Norton resistance Rn, by calculating the open circuit voltage and the short circuit current between the nodes A and B. If we switch off the independent sources in the extreme top left circuit, we will get the circuit given at the bottom. This circuit will contain resistors and dependent sources only. All the independent sources have been switched off and will not show up in this circuit. Similarly, if we switch off the independent source in the Thevenin and Norton equivalent, then both of these will give us the circuit shown on the bottom right, which is simply the Thevenin or the Norton resistance, and both of these resistances are equal. The bottom two circuits are also equivalent to each other. What this means is that if we switch off independent sources, then the resistance between the terminals A and B will be the same for both circuits, and we will be able to calculate RT simply by looking at the resistance between terminals A and B. To summarize, the alternative method of computing Thevenin or Norton resistance is to switch off the independent sources and to calculate the resistance looking in from the terminals A and B, and this resistance will be equal to RT, or the Norton resistance for both circuits. We can use any one of two methods to calculate the resistance looking in between two terminals. The first method is to use a series parallel combination of resistances till we reduce the entire circuit down to a single resistor between the terminals A and B, and this resistance will be equal to the Thevenin or Norton resistance. This method will be useful if we do not have any dependent sources and we can combine only resistances in series and parallel. The second method consists of applying an external current or voltage source of any value at the terminals A and B. For example, if we connect a voltage source, we will get. Next, we measure the current going into the circuit, which will be called I in, and the value of RT will be given by E divided by I in. This second method is useful if we have dependent sources in the circuit. We will apply both of these methods to the same example circuit that we analyzed in an earlier video. In this example, for the circuit on the left, we have to calculate the Thevenin or Norton equivalent between the terminals C and D. The circuit on the right shows what happens when we switch off the independent voltage source, which is replaced by a short circuit between the nodes A and D. We use the first method given above, which is to calculate the resistance looking in from the terminals C and D, which will be equal to RT and Rn. We will redraw the circuit on the right hand side to make it a little bit more convenient to see which resistances are in series or parallel. We will begin with the nodes C and D. The 8 ohm resistance is connected between nodes B and C. We will draw that next. The 12 ohm resistance is connected between nodes C and A. However, A is connected to D through a short circuit, which means that the 12 ohm resistance is connected between nodes C and D, and we will draw it between these two nodes. The 20 ohm resistance is connected between nodes B and D. We draw it next. And finally, the 5 ohm resistor is also connected between nodes B and D, and we will draw it in parallel to the 20 ohm resistance. And we have to calculate the resistance looking in from the terminals C and D. Looking at this redrawn circuit, we can see that there's a 5 ohm resistor in parallel with the 20 ohm resistor. We can write down 5 ohms in parallel with 20 ohms, which will give us an equivalent resistance, which will be the product of these two resistances divided by the sum of the two, which is equal to 4 ohms. This is the resistance looking in between the terminals B and D at this position. We will call it REQ1. Next, the 8 ohm resistor is in series with REQ1, and the equivalent resistance looking in from the terminals shown, we will call this resistance REQ2, and REQ2 is equal to REQ1 plus 8 ohms is equal to 12 ohms. Finally, we have REQ2 in parallel with the 12 ohm resistor, which will give us RT, and this will be equal to the product of the two, which will be 12 multiplied by 12 over the sum of the two, which is equal to 6 ohms. Recall that this is the same value of the Thevenin resistance that we got in an earlier video for this circuit. To summarize the first alternative method of computing the Thevenin or Norton resistance, we switch off the independent sources, and using a combination of series and parallel resistances, we reduce the circuit down to a single resistor, which will be equal to the Thevenin or Norton resistance. Also recall that this first method is useful if we do not have dependent sources in the circuit. We will use the second method given above to calculate the Thevenin resistance between these two terminals. For this method, we can connect a voltage source of any value between the terminals C and D, measure the current going in, and the voltage value divided by the current value will be equal to the resistance. We will begin by redrawing the circuit and connecting a source. The voltage source can have any value. For example, we will choose that E is equal to 1 volt. We will use nodal analysis, select a node as the reference node. There are two other nodes, P and Q, at which we have to calculate the nodal voltages. Node Q is connected to a grounded voltage source, and we can write down the nodal voltage VQ is equal to 1 volt. And we do not write a KCL at this node. KCL at P will give us that the current leaving is Vp by 5 plus the current leaving Vp by 20 plus the current leaving Vp minus 1 divided by 8 is equal to 0. This is one equation in one unknown, and the solution of this equation will give us that Vp is equal to 1/3 of a volt. To calculate In, we will write a KCL at the node Q. This will give us that the current leaving node Q through the 8 ohm resistor will be 1 minus Vp, which is 1/3 of a volt, divided by 8 ohms, plus the current leaving through the 12 ohm resistor, which is 1 divided by 12, minus the current In, which is entering node Q, and this must be equal to 0. The solution of this equation will give that In is equal to 1/6 of an ampere. And the Thevenin resistance will be equal to the voltage source value divided by In, which will give us 6 ohms, which is the same value as we have computed previously. In summary, the second alternative method for computing the Thevenin or Norton resistance is to switch off the independent sources, apply an external voltage or current source at the Thevenin terminals, calculate the input current or the voltage as the case may be, and voltage divided by current will give us the Thevenin or Norton resistance. This second method is useful in particular when we have dependent sources, and we cannot use method 1 because we cannot combine a dependent source in series or parallel combination with a resistance.